Okay, good morning, everyone. My name is Chunhan Feng. I'm a postdoc at CCQ Flatiron Institute. Today, I would like to talk about our recent work on characterizing correlations in the spin-imbalanced attractive Hubbard model, synergy with quantum gas microscopy. First of all, I would like to thank all my collaborators, Professors Shiwei Zhang at Flatiron Institute, Yuanyao He at Northwest University, and also experimentalist Professor Martin Zierlein's group at MIT, and also his postdoc and graduate students, Ningyuan Jia, Thomas, Bertrand, and Carter. Here is the outline of my today's talk. I will start from some background talking about Hubbard model and Q-Praise physics, and then I will briefly show you the model we studied here, and then I will briefly discuss the method, constraint path auxiliary field quantum Monte Carlo method. Later, I will show you some interesting results, including how we characterize the FFL order, and we obtain a phase diagram on the 2D density magnetization plane. And later, I will also show you some interesting results on density-density and single-on double-on correlations, and I will also discuss some finite temperature properties of such a spin-imbalanced system. And finally, I will discuss some other observables we can measure in the experiment to detect the FFL order. And in the end, I will summarize our work. We know the Hubbard model has been used as a paradigmatic model for many years to study the electron-electron interaction. And actually, there are lots of interesting phases can be captured by the Hubbard model, like the antiferromagnetic phase, spin charge straps, and also pseudo gap and strange metals, etc. And this is a schematic doping phase diagram for the high TC cuprate superconductors. And we can clearly see there is a larger regime of D-wave superconductivity in the whole doped side. Actually, when high TC cuprate materials were discovered, there have been debates on whether the Hubbard model can be used to capture the cuprate physics. And recently, there is a work by Professors Mingpu Qin, Shiwei Zhang, Steven White, and Uli Schauwak, and their collaborators. They found there is no D-wave superconductivity in the pure two-dimensional Hubbard model. And then after this, people started wondering, maybe the next nearest neighbor helping T prime would play an important role. So recently, there is another work. People studied the Hubbard model with T prime term, and they found that there is a partially filled strap coexisting with D-wave superconductivity. And here is the phase diagram from that paper. So the y-axis is the D-wave pairing order parameter. The x-axis is the doping. And we can clearly see there is a larger regime of D-wave superconductivity in the whole doped side, which successfully captures the D-wave superconductivity in this Hubbard model with T prime term. Now, let me also quickly show you some interesting results in the literature in the recent years for the pure repulsive Hubbard model. So for example, this one is for the ground state given by the constraint path auxiliary field quantum Monte Carlo method. And here is the staggered spin density along the x direction. And we can clearly see there are two crossings with the zero lines here. So that actually corresponding to the two straps here in the antiferromagnetic pattern, so it reflects a pi phase shift there. And on the right-hand side, it is the whole density along the x direction. So we can also clearly see there are some charge modulations there. And here are also some finite temperature works, and we have already heard from Dr. Alex Witek. And in this work, they look at the magnetic structure factor versus momentum. For the half-filling case, we can clearly see there is a peak at k equal to pi pi, which corresponds to the AFM order. And for a doped system with doping equal to 1/16, we can clearly see when we lower the temperature, there is a peak at 7 pi over 8 and pi. So that corresponds to the AFM straps we have observed previously. And here are also some work for finite temperatures given by the constraint path AFQMC. And here are basically some real space spin correlations. So at relatively high temperature, beta equal to 6, we can only see there is one AFM domain. So the blue up arrows represent positive, and the right down arrows represent negative correlations. And then later, when we lower the temperature, we can clearly see there is a pi phase shift along the boundary. So basically, two AFM regions represented by these two colors here. Okay, so up to now, we have seen there are lots of interesting physics in the repulsive Hubbard model, and we know there is a mapping between the repulsive one and the attractive one. And also, in the attractive Hubbard model, we can use it to study superconductivity. And in the recent years, the pair density waves and also exotic superconductivity have attracted a lot of attention. It describes physics of Cooper pairs with finite momentum. Actually, it can be traced back to 1960s, which was first proposed by Feudal, Farrell, Larkin, and Ovchinnikov. It is called FFLO state. We know the Euro BCS theory describes a phase transition from a normal gas of fermions to a superfluid phase consisting of Cooper pairs with zero momentum. And we can use this mean field ansatz to describe the physics there, and it is position independent. But for the exotic superconductivity, the position dependence of the order parameter is very important. So for example, here is the mean field ansatz for the FF state and LO state respectively. And actually, such an FFLO state can be described by an attractive Hubbard model with a magnetic field, and we have some cartoons here. So due to the effects of magnetic field, we can see the Fermi surface of spin-up and spin-down fermions will be different. And as a consequence, in the BCS picture, the spin-down fermion with a momentum k will be coupled to a spin-up fermion with momentum negative k. But for the FFLO case, a spin-down fermion with momentum k will be coupled to a spin-up fermion with momentum negative k plus q. So the net momentum is equal to q in the FFLO phase. And in the literature, there is also a recent paper studying the ground state of the FFL state using the CPF QMC method. So on this slide, it is the pairing correlations in the real space. The light blue colors represent positive correlations, and the dark blue colors represent negative correlations. So we can see there are modulations in the pairing correlations. The right panel here are just the pairing correlations along the three line cuts here, and we can also clearly see there are some negative values along the edges of this lattice. Okay, so now let's quickly review the model we studied here. It's basically an attractive Hubbard model with a magnetic field, and Ci sigma, dagger Ci sigma are just the creation and annihilation operator, and Ij denotes the nearest neighbors, and T is the helping strength, and the next term is the interaction term, U is the interaction strength, and I sigma is the density operator. And finally, we will also have the magnetic field term and also the chemical potential term. Okay, so we have mentioned several times there is a mapping between the attractive Hubbard model and the repulsive one. But here I also want to emphasize there are some difference. So one thing is most of the studies in the literature focus on the doped spin-balanced repulsive Hubbard model. If we do the particle hole transformation, it will correspond to a spin-imbalanced but half-filled attractive Hubbard model. But we know in the FFLO order, it does not only exist in the half-filled case, but also in a doped system. So it would be very interesting to study the finite temperature properties of such a spin-imbalanced and doped system in the attractive Hubbard model. And correspondingly, due to the mapping, our work should also shed light on the doped, not only doped, but also spin-imbalanced repulsive Hubbard model, which is less well studied in the literature. Okay, so now let me briefly discuss the method we used here. It's basically a finite temperature version of the constraint path auxiliary field quantum Monte Carlo method. It actually uses lots of ideas in the determinant quantum Monte Carlo method. So our goal is to calculate the partition function can be expressed as a trace of e to the negative beta h. And the general ideas is we know we can do a trace of exponential of quadratic form of Fermion operators analytically if the matrix is comprised of numbers. And in the Hamiltonian, the only non-quadratic term is the interaction term. So we just need to do some extra things, which is the Hubbard's Drolthanovich transformation to convert the original many-body problem into many single particle operators. And then after some algebra, we can write out an expression for the partition function, which is equal to a sum of px is some constant times the product of two determinants, one for spin up and one for spin down. In general, there is no special relation between the spin up and spin down part, so it can also be positive or negative. That's basically how the sign problem arises. And we can also understand this more clearly from the cartoon here. So basically, the x represents different configurations we have, and dx represents the weight of such a configuration. There are some positive part and negative part, but most of them will just cancel each other. And finally, only a very small part of it will really contribute to the partition function. And when we really do the calculation, we can also prove there is some quantities when we do the calculation called PL. When it hits to 0, it doesn't really matter what kind of path we choose later after this L. All the parts will just cancel each other. So we need to introduce some constraint requiring all the PL having a positive value. So that's basically the idea of this method. Now let me show you some benchmark for the method. The first one is for the repulsive Hubbard model. And here are two sides of data. One is given by the finite temperature constraint path AFQMC method, and the other one is given by the DQMC method. And we have two temperatures here. So we can look at the first one, beta equal to 2, the green symbols and the red symbols. So basically, they are just on top of each other. And if we look at beta equal to 5, similar things, so it tells us there is essentially no difference between the DQMC and finite temperature CPQMC method. And this size is similar, but we show several different quantities like energy, density, and also density-density correlation and spin-spin correlation. It shows us there is a pretty good agreement between DQMC and AFQMC. So on this slide, we will show a bit more data. It is the energy. So the blue points here is still from the finite temperature AFQMC, and the red data points are from DQMC. So for the high temperature side, we can see basically they're just on top of each other. And when we lower the temperature, look at the two symbols here. We also have some results from 0 temperature version of the AFQMC and also results from DMRG. So basically, it just connects smoothly to the 0 temperature AFQMC1, which is also consistent with DMRG. So all of this tell us the method we used is pretty accurate. And here are some actual things benchmark for our spin-imbalanced system. And it's at T equal to 1/3, and we just look at the magnetization versus magnetic field, and also the single density versus magnetization here. And there are two sides of data. The data points here are given by the finite temperature AFQMC, and the lines here are given by DQMC. And we can clearly see that just on top of each other, a pretty good agreement. Okay, great. Now let me show you some interesting physics results. In order to characterize the FFLO order, the first quantity we look at is the parent correlation in real space. And if we are at some high temperature, if we look at the real space patterns here, the orange points represent positive, and the green color represents negative. At at very high temperature, we can only see there are some only near neighbor correlations. The correlation will decay exponentially. And then when we lower the temperature to 0.67, we can clearly see there is a region of the green colors. So that corresponds to the negative correlations. We start to see the first node of the FFLO phase. And later, when we lower the temperature to T equal to 0.08, we can clearly see on the edges of the lattice, there are also some orange points there. So that indicates the second node of the FFLO order starts to appear. And interestingly, when we lower the temperature, we see a very interesting pattern in the real space. It changes from a diamond to a circle, and then finally to a square. And the second quantity we look at here is the pair susceptibility in the momentum space, which is actually a Fourier transform of unequal time pairing correlation integrated over imaginary time. And for the high temperature case, since only the on-site term dominate, so it's almost uniform in the momentum space. And later, when we lower the temperature, we first see there is a peak here at k equal to 0, 0. And later, when we further lower the temperature to 0.16, we can see the peak position shifts to pi over 8 and 0. It appears at some finite momentum, so that corresponds to the FFLO order. And finally, to a pretty low temperature equal to 0.06, we can see if we look at along the x direction, there is a peak at k equal to pi over 8 and 0. And if we look at along the diagonal direction, there is also another peak here at pi over 8 and pi over 8.
May I ask you, why do you have the picture number 3? Why it's along x and not along y? What breaks the symmetry between x and y?
Sorry, your question is about
Picture number 3.
this one?
Yeah. Why only
Oh.
along x but not along
Oh, so basically there is also a symmetry between the x and y direction. So now I just look at the 1, 0 direction as an example, and there are also some other things along the 0, 1, and this. Yeah. Yeah, so actually the changes of these peak positions are also consistent with the real space patterns we have already seen. It changes from a diamond to a circle and finally to a square. And the third quantity we look at here is the pair momentum distribution. So we can define a pairing matrix for Cooper pairs with center of mass momentum Q, and its leading eigenvalue is denoted as the pair momentum distribution. And we can see some similar features here. So at very high temperature, T equal to 2, the right curve is almost flat in the momentum space. And later, when we lower the temperature a little bit, we can see first there is a peak appears at Q equal to 0, 0. And that's also consistent with the case we have seen in the pair susceptibility one. And later, when we lower the temperature to 0.25, the sine curves here, we first see a peak appears at pi over 8 and 0, the sine curves here. And finally, when we lower temperature to 0.06, we can see there's not only a peak along the 1, 0, but also another peak along the 1, 1 direction. So now we just use the two methods we just discussed to obtain a phase diagram on the 2D plane, density versus magnetization. The results are for several different temperatures. So the first method we used here is by looking at the real space pairing correlation. So the color bar values here represents the most negative value of the pairing correlation in real space. And if the correlation is always positive, we just record that value equal to 0 in the plot. So that means if the value is positive or have some very small negative value, the color would be dark blue. So that indicates there is no FFLO order there. And later, if the value becomes more and more negative, that indicates we can clearly see the FFLO order, the first node of it. So basically, the right-hand side of the diagram is the FFLO order. And the second method we used to find this phase diagram is by looking at the peak positions of the pair momentum distribution. The peak position is denoted as Qx star and 0. So the different symbols here represents the value of this Qx star. So if Qx star is equal to 0, represented by the star here, it just means the peak is at 0, 0. So there is no FFL order. And if it is at some finite momentum represented by the other symbols here, that means there is FFL order. And basically, the results given by these two methods are also consistent with each other. And the dashed lines here are just a guideline to the eyes. And interestingly, or unexpectedly, we can also see the signature of FFLO in a pretty high temperature at T equal to 0.33, and it's already within the experimental reach. So besides looking at the pairing correlations, it's also interesting to explore some other correlations. So on this slide, I will show you some results for the density-density correlations. The upper panels here are all from experiment, and the lower panels here are from simulations. And we can see there is a one-to-one correspondence between them. In general, it shows us a pretty good agreement. And we can also see some interesting physics here. So for example, at density around 0.77 and smaller magnetization case, we can still see there are some short-range CDW patterns here. And then later, when we increase the magnetization, in this case, it behaves more like a Fermi-liquid behavior. So basically reflects the Pauli exclusion between the on-site and nearest neighbor terms. And similar things for the second rows here, when density is a little bit smaller, around 0.6 or something, we can see a much weaker CDW pattern. And then when we increase the magnetization, we can also see the effective repulsion there due to the Pauli exclusion. And on the right-hand side, we just plot the same quantity, the density-density correlation versus magnetization by using some lines and data points here. The lines are the results from the simulation, and the data points are the results from the experiment. And the color bar values here represent different densities. So in general, the three panels here represents results at different size, 1, 0, 1, 1, and 2, 0. And in general, we also see a pretty good agreement between the simulation and experiment. Yeah, question.
What is the temperature that you took this
this
simulations?
One, yeah, this one is at T equal to 1/3.
Thank you.
Yes. Yeah, so in a spin-imbalanced system, it's also interesting to explore the single-on and double-on correlations. And the single-on actually refers to the unpaired fermions. So here is the definition of the single-on density. It is equal to spin-up density minus double occupancy. And we can also see some interesting physics here. So for the density around 0.77 and small magnetization case, we basically can see the Pauli exclusion between the spin-up fermions in the single-on and the spin-up fermions in the double-on. So it is an effective repulsion between them. And when we increase the magnetization, as we have heard from Martin's talk, if we have many spin-up fermions and there is only one spin-down fermions, the spin-down fermion will just behave like a free fermion. It just can help to any arbitrary size, so it can increase the kinetic energy of the pairs. So finally, we can see there is some effective attraction between them. And at some intermediate case, there is basically a competition between these two effects. And similar things, we just present our data by using some lines and data points here, and we can also see a reasonable and good agreement between the simulation and the experiment.
Okay, well, the last column doesn't look the same.
Yeah, so you mean things like here and here. So yeah. So basically, I think we didn't do any special things. It is just a direct comparison. So I mean, in the experiment, there are also some traps. So it means the density is probably not uniform, although we look at the nearest neighbors. So maybe that effect is not that strong, but there are maybe some also sort of that effects there. And also the temperature I told you is around T equal to 1/3 is also estimate from the experiment. So it's just an estimate value. It can also change a little bit. And also more or less, and I think it's also depending on the ways we present the data here. So in the color map here, we just plot the mean value of that quantity without showing you any information about error bars. But if you look at such a plot here, you can see for some data points, the experiment data have a relatively large error bar. Sometimes they are just sit across the zero lines here. So that means sometimes it's positive or negative, and we can clearly not tell that. Yeah, but in general, I think the trend is still pretty clear. We can see similar things. It changes from some blue color to red one. Yeah, so that's something consistent. Yeah, great. So we just mentioned the results we have seen is at some finite temperature, T equal to 1/3. It would also be interesting to explore how these patterns would evolve with temperatures. And on this slide, I will just show you the density-density correlation and the single-on, double-on correlation changes versus temperature. And interestingly, for the density-density correlation one, we see there is a relatively weak CDW pattern at some intermediate temperatures. And for the single-on and double-on one, due to the competition of those two effects we just discussed, we see there is a staggered single-on and double-on pattern at very low temperature. So it would be interesting to explore the finite temperature properties of such a system and see, for example, in which temperature regime we can see such a short-range CDW pattern in the spin-imbalanced system. So now I will just discuss some finite temperature properties of the system. The first quantity we look at here is the double occupancy. And interestingly, we can see there is some non-monotonic behavior in both spin-balanced and spin-imbalanced case. And later, I will show you many results. On the left-hand side, it will always be the spin-balanced case for m equal to 0. And on the right-hand side, it will always be the spin-imbalanced case with magnetization equal to 0.15, represented by the blue curves here. And in the left panel, the blue curve here is actually exactly the same as the one in the right panel. I just put them in the same plot for comparisons. And in the insights here, we just plot the same quantity D versus T, but just using a linear scale for the temperature so that we can clearly see the non-monotonic behavior here. And actually, such an non-monotonic behavior have also been seen in the repulsive Hubbard model at half filling when U is equal to 2 in this paper by Professor Anton Georges and his collaborator, and by using many different methods. And we know there is a mapping between the repulsive one and the attractive one. So if we do the particle hole transformation, for example, on the downspin, the double occupancy in the repulsive Hubbard model will be mapped to spin-up density minus double occupancy. So as a consequence, we expect to see the double occupancy should behave inversely. So I mean, when we lower the temperature, it should goes up and then goes down and then goes up again. Yeah, and by the way, the repulsive Hubbard model is at half filling, and for the attractive one, we not only say this at half filling, but also in the doped case at the density equal to 0.7. And for the spin-imbalanced case, we also see some interesting behavior. In the low temperature region, we didn't see a clear growing up in the double occupancy. Instead, the double occupancy is just suppressed in the very low temperature regime, probably just due to the formation of pairs with finite momentum. Oh, by the way, I just also used some different notations here to represent different temperature regimes. So the T star in both plots are the peak position of the double occupancy, and the TC in the left-hand side is just the BKT phase transition temperature in the spin-balanced system. And TC prime is something I call the FFLO temperature, below which we see the formation of pairs with finite momentum. And later, I will also show you more results on this. And on this slide is some results for the pairing structure factor versus T. And around TC, we can see there is a sharp increase in the pairing structure factor at K equal to 0, 0. And at all these temperatures, the value is always larger than the pairing structure factor at other K points, for example, pi over 8 and 0. And for the spin-imbalanced case, we can see around this TC prime, the pairing structure factor at pi over 8 and 0 grows much larger than the one at 0, 0. So basically, this below this TC prime, we know there are some pairs of finite momentum formed. And on this slide is the spin susceptibility versus T. And you know in the literature, we always view the peak position of the spin susceptibility as the pseudo-gap temperature. And actually, in our case, this peak position is exactly the same as the peak position in the double occupancy versus T. So basically, it is just this T star is the pseudo-gap temperature. And later, when we decrease the temperature, we can see there is a sharp decrease around this TC. And finally, below TC, spin susceptibility just almost vanish. And as a contrast, for the spin-imbalanced case, we can see when T is larger than this T star, so basically it just follows the same line for the spin-balanced case. They just behave similar to the spin-balanced one. And later, it will further increase to some maximum at this TC prime, and then finally decrease. And then later, in the pretty low temperature, it remains at some finite values, probably due to the excess fermions we have in the spin-imbalanced system. And now,
Question?
Yeah.
If I'm not mistaken, FFLO transition is first order. Do you see any evidence for that?
See evidence for
FFLO transition to the FFLO state, as far as I know, is first order.
I think
Do you
that's
see any
really
evidence of that?
Yeah, that's a really good and pretty hard question, I think. So basically, I think for the spin-balanced case, we can really do some things like finite set scaling using some critical exponents to do some data collapsings to get this TC value. But for the spin-imbalanced case, based on my data, it seems like the pairing correlation decays actually pretty fast, at least a power law decay, or even faster than that. And also, as we have already seen from the previous slides, the peak position of the pairing structure factor also shifts a little bit when we lower the temperature. So it's probably not easy to tell which structure factor at which K point we should look at and how to do the scaling things, etc. So yeah, I think that's some question, for the future.
Yeah. So just to clarify, the K that's used in the top formula, that's the peak, or?
The K here?
Yeah.
Yeah, it's just the momentum. Yeah.
And the value you're plotting?
Oh, you mean something like in the previous slides, this K value?
It's well, the top equation was a function of K.
Oh, thanks for the question. I think for this one, it's just a K equal to 0, 0. Yeah, thanks. Yeah, both sides. Yeah. Okay, great. So now let's quickly look at the CDW structure factor. And as we mentioned, we have already seen some short-range CDW patterns in the spin-imbalanced case. And let's examine this more carefully. So the first one is for the spin-balanced case. The structure factor, CDW structure factor, is represented by the black curves here. And we can clearly see there is a jump in the CDW structure factor between this T star and this TC. So basically, the so-called pseudo-gap regime. And here are also some real space patterns. And we can also clearly see there are some short-range CDW patterns at these intermediate temperatures. And if we focus on some correlation, density-density correlation at 1, and plot it here, I just shifted it a little bit to plot them in the same plot here. The zero line is represented by the dashed line here. So we can see there is a large dome in this middle region. So that indicates there are also some short-range CDW patterns in the spin-balanced case in the pseudo-gap regime. And for the spin-imbalanced case, as we have seen previously, there is a much weaker CDW pattern also in this pseudo-gap. Maybe we should not call it pseudo-gap anymore in this intermediate temperature regimes, but it is in a much more narrow region, and the amplitude is also much smaller than the other one. And finally, it is just the single-on and double-on correlation, and we have already seen some information about this. And if we look at how this correlation changes with temperature, we basically can see when T is larger than T star, only the nearest neighbor term 1, 0 dominates in the system. And then between T star and TC, we can see the correlation becomes stronger and stronger in both cases. When T is smaller than TC or TC prime, the magnitude just becomes almost flat. And here are the patterns for the spin-balanced one. So basically reflects the Pauli exclusion, and this is the pattern for the spin-imbalanced case. So basically reflects the competition of these two effects we just discussed. So now we have discussed lots of interesting properties of such a spin-imbalanced system. And another useful question to think about is whether there are some other observables we can measure in the experiment to detect such a FFL order. And in the repulsive case, we know when there is AFM stripes, at the same time, we also see there are some charge modulations. And as an analogy, in the attractive case, when we see some FFLO order modulations in the superconductivity, it's also possible to see some modulations in its particle hole transformation partner, which is the spin X and spin Y correlations. So on this slide here, we just examine the spin X and spin Y correlation and the pairing correlation, and we just show the sign of them along the lattice. And at high temperature, T equal to 2, we can see the wavelengths for the pairing correlation is much larger than the wavelengths for the spin X correlations. And when we lower the temperature a little bit, we can see the wavelengths for both also decreases. And interestingly, in the pretty low temperature here, we have T equal to 0.125 or much lower, this one here. Finally, we see the wavelengths for the pairing correlations and the wavelengths for the spin X correlations also become the same. So it might be also interesting to explore this in the experiments, and our collaborators, Martin, also considering measuring this in the experiments. So probably we can use it as a proxy to detect the FFL order. And here are just some actual results for different lattice size. So this is for 32/6 lattice. And the colors of the background, the circles represent the pairing correlations. So the cyan color represents the positive one in the middle region here. And the blue color of the background represents the negative one. And the arrows here represent the sign of the spin correlations. So right down arrows represent negative, and the blue up arrows represent positive ones. And we can see similar things in the ground state. Basically, they will have the same wavelengths in these two things. Yeah, these are just more results for another different lattice, 32/8. and 32 by 8, pretty low temperature. So for the low temperature one, we can see the pairing and spin-X correlations have the same wavelengths. Okay, great. To summarize our work, we just look at the real space pairing correlation and pair susceptibility, and also pair momentum distribution to characterize the FFLO order. And then we obtain a complete phase diagram on the 2D density versus magnetization plane. And we also look at some interesting correlations, density ones, and also single and double on ones. And later, we also discuss some finite temperatures properties of such a system. For example, there is a non-monotonic behavior in the double occupancy, and there is also some short-range CDW patterns at intermediate temperatures, basically in the pseudo-gap regime. And finally, we just show there is a close connection between the spin-X and correlations and the FFLO order, and we probably can use it as a proxy to detect the FFLO order. Okay, thanks for your listening. I would like to take any questions you may have.
Thank you, Chunhan. Questions?
Yeah.
One question that I have is very interesting talk. Thanks, by the way. When you look at the BKT critical temperature and the FFLO critical temperature on one of the slides back, anyway, or slide 24, whatever. Oh, here there it is.
Yeah.
I'm surprised that the critical temperature for FFLO would stay so high. I would expect that as you asked imbalance and your pairing only happens at particular edges of your Fermi surfaces, that it would drop well below the BKT transition temperature. Do you have an understanding for that?
That's a pretty good question. Thank you for the question. So basically, for the spin-balanced case, I think in the community, in the literature, we know the answer pretty well. So basically, this TC is really the critical temperature of this superconductivity phase. But in the spin-imbalanced case, as we have previously discussed, I don't think there is a very clear definition for the critical temperature for the FFLO order. And instead, that's why I also call it TC prime here. So basically, this is just the temperature below which we can see there is a formation of pairs with finite momentum. So basically, it's this temperature where we can see the pair structure factor at other k points grows larger than the pair structure factor at k equal to 0, 0. But I'm not quite sure whether we will call it critical temperature. So that's probably the reason.
Thank you.
Yeah, thank you.
Perhaps one could go a little bit stronger. This is almost certainly an overestimate because one is reading off the first node of crossing in a finite system.
Great joke, wonderful, Chunhan. I just wanted to know, what is the largest system you can do?
So for the square lattice, most of the results are on the 16 by 16 square lattice. And for the long cylinder results, where I show you pairing correlations and XY correlations, the lattice size is like 64 by 4, and also some 32 by 6 and 32 by 8.
And so far, is 16 by 16 kind of an intrinsic limitation, or with more computer time, you could go to larger sizes?
Yeah, we can probably do a little bit larger, maybe 22 by 22, something like that. But that's, very close to the limit.
Can you give me an idea of the computation time for 16 square?
For
one, right? Converging the wave function.
So I think for the very low temperature case, for 16 by 16, it may take like 2 days or so.
Okay. On how many processors?
Like 40 workers, and on each worker, I think there are 40 CPU cores, something like that.
So it's a parallel scale. So I would it's easier for me to say. It's a lot bigger.
How does that scale?
You mean?
With the size of the system?
Oh, I think it should be N cubed times the imaginary time slide. N cubed times L. L is the imaginary time.
Okay, thank you.
In a way, a metaphysical question. I don't know if it can be formulated in a way which is quantifiable. As you showed comparison of the positive view and the negative view, and as we discussed before, there is a mapping. On the practical calculation, do you see a difference in the difficulty of simulating either the positive view or the negative view? Or at the end, is it the same problems that show up in a different way that make the life miserable practically at the same values of the parameters? Or and I don't know if one can make this question more precise because.
So yeah, thank you for the question. I think basically for our simulation, there is no difficulty to simulate either the repulsive view or positive view side. And the only difference here I mentioned in the several slides before that is I think in the literature, most of the studies still focus on just the dope, the spin balanced case in the repulsive one. So that will correspond to the spin imbalanced and the half filled.
But if you are spin imbalanced and away from half filling, that should be the very difficult region in the positive U side, which has sign problems and everything. So something similar should happen to you in the negative.
Yeah, so I mean, so currently we just study the spin balanced and doped system in the attractive one, and that will correspond to not only doped but also spin balanced in the repulsive one. So they are equivalent. Yeah.
Follow-up question to Antoine. You said the scaling is n cubed, which is another way of saying that you don't have a sign problem. It's actually not exponential in complexity. Can we take this home as a message? Like, you now know the Fermi-Hubbard model is not exponentially hard, or is it just a technique and there's an assumption that underlies this?
Oh, so basically, I think the algorithm scales as n cubed L is not only true for this constraint path FTF QMC method, but it's also general true for the determinant quantum Monte Carlo method DQMC1. So the reason that it scales similar to that one is just that we introduce some constraint here to avoid the sign problem. I mean, the Euro DQMC one, although it scales as n cubed L, but the number of sweeps, when there is a very serious sign problem, the number of sweeps we need to do would be exponentially large to make the error bars become smaller. Yeah.
Yeah. They are fundamentally different. This is an algebraic scaling algorithm, but at the cost of an approximation. It's an approximate calculation.
The question then fundamentally is, I guess, whether the approximation is controlled or we don't know.
Sort of controlled in the sense that
We may know how.
Okay. Yeah, thanks.
it's a longer discussion, maybe better for the next session. It's sort of controlled in that we've accumulated a lot. We have dials we could dial up at more cost. So we could trade accuracy for more cost. Eventually, of course, you could trade back the exponential cost, but maybe with a much better prefactor.
I see.
But in between, we have stops, stations, refueling stations that do really well. And that's the empirical knowledge through benchmarks and so on.
It could be a stupid question. So, in your calculation, can you calculate the superfluid density? So, can you do that?
Yeah, I think we can also calculate that.
So, is it difficult? I mean, because for example, if you want to say FFL, I mean critical temperature, maybe the best way is just to calculate the superfluid density. So if it's non-zero, so you have the transition, right?
I think that's some interesting.
System, if it's not zero in finite size, it's not PCA.
Yeah, so anyway, I think in our algorithm, we are able to calculate that, and that's probably also some interesting to explore, yeah.
Take one last question, please.
I would like to ask about the influence of the density in addition to the magnetization. So you've, of course, showed how these things are scaling, but is there a general statement about whether higher or lower densities have some advantages or disadvantages to see this type of phase? And in connection also, how much does the interaction then matter? Because I assume when the density is lower, maybe one needs more interaction to see something.
Yeah, that's a great question. So let's go to the phase diagram one. Okay, yeah, this one. Yeah, so basically, I think this is a complete phase diagram. So basically, for the FFLO order, it seems like it exists almost at very wide range of densities. And for the other things, for example, like the short-range CDW pattern, I think those probably will mainly exist in the larger density regime, maybe around 0.7 or larger. So when density is not that low, some short-range CW patterns will be there. But FFLO order should also exist in other densities.
I mean, in reverse, I would conclude now that if we go on the repulsive side and give it some magnetization, we should also see already some stripes at these temperatures of, what is it here, 0.3 T.
So your question is, at this temperature in the repulsive case, whether we will see some stripe? Is that your?
Well, that's kind of what I'm concluding. I'm just normally not used to the area where there's this density change / magnetization on the repulsive side. And so, of course, my motivation as an experimentalist would be now, is it worth for me to start magnetizing my repulsive system to start seeing some stripes order at higher temperatures?
Oh, okay, I see. I got your point. I think the main difference here is it is not only spin-imbalanced here. So if it's a half-filled spin-imbalanced system, I think your conclusion will be directly correct, since there is a direct mapping between these two. But in our case, since it is at some doped system. So for example, at different densities. So that means it will correspond to the spin-imbalanced Hubbard model at some doped case. Yeah.
I think that's the point you're trying to make.
Thank you.
Maybe it's better to carry the discussions over to break. Let's thank both speakers again.